So this question is number of provinces. Now, a province is a group of directly or indirectly connected cities and no other cities outside of the group. So we do understand directly connected cities, but indirectly connected cities is when A is connected to city B, which is then connected to city C. Then that means that city A is indirectly connected to city C. And at the end, we just have to return the total number of provinces. So I'm using the union find data structure over here. Firstly, start with declaring parent. So parent of I says who is I's parent in the tree. So initializing it to 0, then 1, then 2, all the way up to n minus 1 means that every node points at itself. Each city is its own root. Then rank is 0 times length of is connected. So an upper bound on each tree's height. And all trees start as single nodes, so height is 0. Then count is set to length of is connected. So this is a running answer. Then this is the classic find function. Now the loop is the definition of root. So a node is the root exactly when it is its own parent. So we climb until that is true. Then this is path compression or path halving. So before moving up, we repoint X directly at its grandparent. X's old parent is still a valid ancestor of the same root. So this does not change the answer. It just skips a rung. We do this repeatedly across many calls, and long chains collapse into short trees. Then this is the union function. Did I miss anything? Oh, yeah. Now, before moving up, we move to the new parent, so the grandparent, which is why the path shrinks by half traversal over here. And returning the root is the point. So two nodes are in the same province if it returns the same root for both. Yeah, now the union function. So this non-local count we have declared outside. It's important to use non-local over here because without it, Python will treat count as a fresh local variable. So you would get an unbound local error. Then RA equals to RA equals to find A, RB equals to find B. So if roots over here, if roots already match, so if RA equals to RB, if roots already match, A and B are already in the same province. So this edge is redundant. We return without touching the count. Then if rank of RA is less than rank of RB, so this is union by rank or union by size. So we are about to hang one tree under the other, and hanging the shorter tree under the taller tree keeps the result short. So this swap is guaranteeing that RA is the taller root. So the next line doesn't need two branches. Then parent of RB equals to RA, so the merge itself. So one pointer right, RB stops being a root and becomes a child of RA instead. And then if rank of RA equals to rank of RB, now this is the height bookkeeping. If RA was strictly taller, hanging RB underneath doesn't make the tree any taller. So the height is unchanged. And only when both were the same height does the combined tree grow by one level, which is happening over here. And then count reduces by 1, so we just fused two distinct provinces into one. So the total drops by exactly 1. And now this is the main loop. So j is starting at I plus 1. This restricts us to the strict upper bound triangle. And then the diagonal is always 1. And so union of I and I would find equal roots. And then we have is connected of I and j. And then we will pass the union function and we pass I and j. And this j loop runs all the way until length of is connected. At the end, we are just going to return the count.